All right, thank you. Thank you for the introduction. And again, thank you and Eric, who's not here now, for organizing network seminars all year long. It was super fun. So thank you very much. And you handled even this situation very well. All right, so hi everybody. I'm Nicola. I just joined the group here in Oxford. And today I'm going to talk about this work who was recently published. It's work I carried out during my PhD in Marseille, together with my two supervisors, Alain Barram and Damien Battaglia. And well, the title of the work is The Temporal Rich Club Phenomenon. How do I just click or? Nope. Oh yeah, here it is. All right, so very quick introduction about what the traditional definition of rich club used to analyze static networks is. Well, the motivation behind it was due to the fact that in many real-world systems that we can describe as networks, we find heavy-tailed degree distributions, which means that the majority of nodes actually have very few connections, and then there's a pretty small minority of nodes that have many connections, many links. And the question at the time was, do nodes with very high values of degree are they also highly interconnected among themselves? Do they form highly connected structures among themselves? And in order to do that, the approach was to define a subset of nodes with degree larger than a certain threshold value, k. And then, so for instance, we're trying to see whether there is a structure like this in a network. So we define our set of nodes of interest as larger than k, as nodes that have degree larger than that threshold. And we look basically at the density of the links connecting them. So this is the definition of the rich club coefficient. So the density, the number of edges connecting them divided by the maximum possible number of edges that could connect them. And in order to tell whether this is something that could not just arise from chance, this was compared to the same measure performed on a random null model. And this led to the definition of the rich club ordering. And these measures were used to try and tackle this question in several different contexts. Here, I show the distribution of the values of the rich club coefficient for an air transportation network in the US, and the relative rich club ordering here on the right. So the rich club ordering, when it is 1, it means that there is no significant difference between the original data, the original network, and the random null model. When it rises above 1, then we do have a rich club ordering. And well, the motivation behind our work was that this measure was used to analyze several real-world networks that actually correspond to the aggregate network of systems that now are available with a much higher temporal resolution. So systems are actually temporal networks. So the question that we wanted to ask was, let's look at the temporal network, the corresponding temporal network, and ask whether these nodes that are highly central in the aggregate network are ever actually simultaneously connected throughout the time evolution of the temporal network. So again, we define the subset of important nodes in the temporal network based on the relative aggregate network. Again, we set a threshold on the aggregate degree k, and this way we select the nodes of interest. And what we do in order to see whether they are ever actually simultaneously interconnected is we keep track of, can you see it here? How do I move this? The chat and okay. All right, thanks. So what we do is actually we keep track of the links connecting the nodes in this subset as larger than k, inserting though this new parameter delta, which is nothing but the length of a time interval. And so starting from, for instance, this snapshot, this timestamp of the evolution of the network, we keep track of the links connecting the nodes in our subset of interest that last throughout the whole time interval delta. Okay, so if delta equals 1, we're looking at the instantaneous density of the subset S larger than K, which, by the way, I would like to stress that it's different than computing the static rich club on each instantaneous snapshot, because on each instantaneous snapshot, the rich club based on the instantaneous degree of nodes can fluctuate from a snapshot to the next. Whereas in this case, we're looking at the same nodes throughout the whole evolution of the network and keeping track of the links, of the durations of the links connecting them. So if delta increases, then we only keep track of the links connecting the nodes in S larger than K that last for instance, delta equal 2 or delta equals 3 and so on and so forth. So this leads naturally to the definition of the introduction of the cohesion of the subset S larger than K at any given time t, which is a value that depends, it's actually a time series of values that depends on both the threshold on the aggregate degree K and the time interval length delta. And this again is the overall density of the links that last throughout all of delta. And the idea is that if we do indeed find a group of nodes with high values of aggregate degree and high values of cohesion for different values of delta, we call this a temporal rich club pattern. And what we can do then is have these pretty drawings here. This heat map actually is the epsilon, the cohesion at for different values of delta. On the x-axis here, we have time for specific values of the aggregate degree. I'm not telling you what network we're looking at right now. I'm just setting up our measure here. And so this basically, depending on the values of K and delta that we choose, these can, for instance, allow us to distinguish between patterns of temporal rich clubs that are more persistent. As you can see here on the right, for this value of the aggregate degree equals 350, we have for delta equal 1, so instantaneous density, pretty high values throughout the whole evolution. And even as delta increases, we have high values. So this seems to be a rather persistent temporal rich club pattern throughout the whole evolution of the network. Instead, here we have, for actually higher values of the aggregate degree K, we have more fluctuating values of the instantaneous cohesion. So again, the orange line is the cohesion for delta equal 1, which suggests that there are moments in time in which this structure actually appears and it's quite cohesive instantaneously. Even for as delta increases, you can see here we actually have basically these curves for every possible value of delta, and you see these triangular shapes here. These are moments in which this structure actually is formed and persists for rather short times actually. And this, we could refer to this as overall transient temporal rich club pattern. But then the question is, for any given pair of values of delta and K, we have basically a time series of cohesion, right? And instead, we would like to condense, if you wish, the information for any given pair of values of delta and K into one single number and call this our temporal rich club coefficients. And our choice was to take the maximal cohesion over time for the corresponding values of the threshold on the aggregate degree K and on the time interval length delta. And this basically gives rise to this sort of parameter space sweep, where we have the heat map. The value on the heat map is actually the maximal cohesion, so the temporal rich club coefficient for every possible value of the time interval length delta and aggregate degree K. So this allows us already to have a look at what structures of this kind can arise throughout the evolution of the network. The question that remains unanswered by now is, how can we be sure that what we're measuring here is not something that could be measured just by chance, right? So we also need to compare this analysis to sorry, I don't know whether I should stand or sit. Okay. And so in order to do this, we need a null model. And our choice was to use a null model that basically preserves all the aggregated statistics of nodes, so preserve basically the structure of the aggregated network. But what it does reshuffle is the timestamps of the temporal and instantaneous edges between two nodes, but preserving the overall timeline of activity of the network. So the instantaneous number of edges on each time snapshot of the network is preserved, as much as the aggregate degree of nodes is preserved. So really what we're trying to disrupt with this randomization of the data is just the simultaneity of the connections between the nodes, right? Or rather the time ordering, which should also disrupt the simultaneity of the connections. And so we do this. So just by looking at these two heat maps, it's quite hard to, just by eye, recognize whether they're different or not. So we introduced the temporal rich club ordering, which is merely the ratio between the maximal cohesion at a given value of K and a given value of delta, with the maximal cohesion computed for the randomized version of the network at the same values of K and delta. So this is our mu. And then we can see whether actually there is a temporal rich club ordering or not. Here we see that for lower values of K, we have values of mu that are actually way higher than 1. Then it gets closer, even though not exactly equal to 1, for higher values around this area here, which corresponds to these patterns here, which we will investigate further later on. And then here we have this increase here. So now we have all of the ingredients that we need to start using this measure and on actual temporal networks. So let's see what this network that I showed you so far actually is. This is the air transportation network in the US, right, where we looked at 1,920 airports in the US. These are the overall statistics or some properties of this network. And looking at the K delta diagram of the maximal cohesion, we see that there is a tendency for nodes with lower K, so with lower aggregate degree, there is a tendency to have some values of cohesion for very short periods of time. But then this, the maximal cohesion actually goes down very quickly with delta, okay? Which means these are not really stable connections. And this can be due to the fact that small airports actually have more fluctuating activities. And some of them can be even seasonal airports, which means that only for 1, 2, or 3 months they're actually active, and most of the time they're not. So this leads to actually a much less stable overall cohesion for these values of K. But as we increase the aggregate, the threshold in the aggregate degree, we see the emergence of this pattern here. So actually here we have airports with aggregate degree larger than 315 that include real hubs of the US air transportation system. And here we notice that for very low values of delta, we have very high values of cohesion, even cohesion up to 1, which means that there are 1 month or 2 consecutive months in which this structure is basically fully connected, all right? And simultaneously fully connected. And even as delta goes on, basically throughout the whole, spanning throughout the whole lifetime of the whole temporal network that we're looking at here, it stays pretty high. And interestingly, as we go further to higher values of the aggregate degree, actually this cohesion is lost. So what is happening here? Like the aggregate degree is higher, but the structure involving these nodes is actually less cohesive. So in order to investigate this, we had a look at what these nodes over here are. And so basically, if we look at the top 20 airports in terms of the aggregate degree, we find these airports here. In red are airports that are actual hubs of the US air transportation network, whereas the blue ones are actually reliever airports. So airports that serve as relievers when there's a neighboring hub that is in need of help, basically. So this leads to the fact that the overall aggregate degree is higher because it has higher variability of connections throughout the evolution of the network, right? So if you look at this in further detail, again, here we have the K delta diagram of the cohesion. Interestingly, this difference between real hubs and reliever airports cannot really seen just by performing the static rich club analysis on the aggregate network, because really what is being lost is the simultaneity of the connections, not the aggregate connectivity of these airports. And the reason why mu has this weird tendency here is that, however, even though there is a less stable and less persistent structure here, it's still much more cohesive than it would by chance, all right? So that's why we have this increase here at the very end. So this is also a suggestion of the fact that the temporal rich club ordering and the temporal rich club coefficient should be looked at together at the same time, because they can tell different stories. And in further detail, if we look at, for instance, the O'Hare International Airport, which is clearly a very big hub, real hub of the US air transportation network, and the Westchester County Airport, which interestingly is the node with the highest value of aggregate degree. If we look at the time series of their instantaneous degree, they're actually quite stable, even though there is a significant difference between them, but they're all quite stable. So they're not, one is a stable hub and the other one is an unstable hub. The key difference between them is we actually understand it if we look at the Jacquard index between one snapshot, instantaneous snapshot, and the next of the neighborhood of that node, the Jacquard index being a measure of similarity, if you want, of the connections between two neighborhoods or two networks. So you see that actually O'Hare has a pretty stable neighborhood throughout the whole evolution of the network, and instead, Westchester County Airport, experiences of pretty high fluctuations of its instantaneous neighbors, right? Which is actually the reason why the aggregate degree, the overall aggregate degree is very high, because throughout the evolution of the network, it is connected to many different hubs, other airports, because the flight needs to land in Westchester County Airport instead of the neighboring hub. Interestingly, we decided to look at what happens if we merge every single reliever airport with the corresponding neighboring hub. And what happens is that the tendency that we saw before disappears. And this is not necessarily surprising. We see that basically we do not have a disruption of the cohesion for high values of K. And this is also the comparison between the data and the random number model for the cohesion at 350. And again, if you look at the static rich club, there isn't much difference between the static rich club in this case and the previous case, right? So actually we have the exact same static rich club, which actually hides two very different temporal rich club patterns. And so really the patterns that we saw earlier are really due to the coexistence of hubs and relievers. So going on, we decided to tackle different contexts also, and we looked at face-to-face interactions in a social context in a primary school. Here we looked at interactions between students and teachers in a primary school in France. And what we saw here is that indeed there is a temporal rich club phenomenon, or pattern, even though with lower degrees, lower values of cohesion. The other interesting fact is that this structure here, so nodes that have aggregate degree equal to 87, are only actually interacting for longer periods of time during lunch, actually. Okay, so this is a suggestion of the fact that the nodes, the kids, the children, the students that belong to this group of nodes are actually belonging to different classes. So they can only interact when the classes are merged together. So either during recess or during lunch. And as you can see, actually, there is a pretty big difference between taking into account the simultaneity of the connections of this group of students with the corresponding static rich club computed on the relative aggregated network. So here again is to stress the fact that these interactions happen during moments of recess and lunch. Here, what you're looking at is the cohesion epsilon in time as a function of K for fixed values of delta. So this would be the instantaneous cohesion, which doesn't vanish for deltas until delta equals 10. And here we see that in the shuffled or randomized version of the network, this structure is actually lost. Now, if you think about it, these students are students that have very heterogeneous connections throughout the whole day. Somehow, in a way, popular kids in the school. So the question is, what happens if any of these children are infected by some disease? How does this structure here influence, what's its relation to the spreading of a disease in this context, or it could even be the spreading of information, actually. So really the next question is, do temporal rich cloud patterns have any impact at all on processes unfolding on top of a temporal network? In order to tackle this question, what we looked at the SIS and actually SIR models for spreading processes. Looking at the SIS, lambda is the probability of infection, nu is the probability of recovery. And basically what we did is we designed or devised an ad hoc null model in which we only take the subset, the subgraph of nodes s larger than k, and we only randomize that subgraph. So we basically disrupt just the simultaneity of the connections of the nodes belonging to that group. And then with the help of this reference here, we compute the epidemic threshold of the SIS model. And we compare the epidemic threshold in the real data to that computed for the randomized version. And the interesting thing is that, first of all, it is lower than 0, this value here. So the difference between data, the relative difference between the epidemic threshold in the data and the randomized version is lower than 0 for every value of the aggregate degree. It stays so even for very high values of aggregate degree. So in a way, this is a proof of the fact that simultaneously cohesive groups of central nodes can actually foster the spreading or affect in general the spreading. So very quickly moving on to the very last data set that we analyzed through the lenses of temporal rich club. We looked at neurons in the medial internal cortex and the hippocampus of anaesthetised rats. This data set actually comes from another work that we did previously during my PhD, and we only took one recording. So basically here we have firing patterns of individual neurons, either in the hippocampus in blue or in the internal cortex in orange. And we compute the mutual information between the firing patterns of each pair of neurons within a time window of 10 seconds, and then we slide it by 1 second. So overall, the time resolution of this temporal network is 1 second, and the length is this here, 2,284 seconds. And we see indeed one temporal rich cloud pattern here. We see this high values of cohesion, of maximal cohesion arising, especially for nodes with very high values of aggregate degree k. Actually, here we have a group of 8 neurons that have the largest degree that are so strongly interconnected that you see that here we're only looking at cohesion values up to 0.5, and it stays so throughout the whole evolution of the network, actually, or almost. Actually not, because in these kind of networks, we're also interested in trying to understand whether there are any states that these sort of networks explore or that affect or describe the evolution of this network in time. And we can see these states as these blocks in this dynamic functional connectivity matrix, which is nothing more than a similarity matrix, which basically each element of this matrix ij or t star is the amount of similarity between the instantaneous snapshot of the network at time t and the instantaneous snapshot of the network at t star. So basically these red blocks here are moments in time in which the network is very has high values of self-correlation in a way, or self-similarity. And therefore, if each of these is understood as a state, we see that there's only one recurring state, which is this Windows symbol-like area of the matrix. So by performing some hierarchical clustering onto this matrix, we actually extract and retrieve the network states of the evolution of this network. And we want to see whether this structure here plays any role in any of these states. Is it state specific? Is it something that is persistent throughout the whole evolution of the network? And actually we see, so this is actually the same group of nodes that we're talking about here. And we see that it's mostly cohesive during one specific state. Okay, so the temporal rich club that we find in this network seems to be very state-wise in a way. This leads to the question, may Actually, before I go into that, just to show you another couple slides on what happens when we compare the data, the actual data with the randomization. So the states are somehow present in the randomization, but actually they're not as present, let's say. The maximal cohesion in the randomized version of the data is basically lost, is completely disrupted. And here it's possible to see that even when looking at the the cohesion for different values of the aggregate degree at fixed values of delta, and you see how with delta equal 1, so the instantaneous cohesion is pretty high for nodes with high values of degree, then it stays high for this group of nodes in this very specific moment in time, even for delta equal 120, so basically 2 minutes. Whereas if you look at the randomized version of the data, there is something only for delta equal 1, and already for delta equal 5, we have nothing, which is why we can't really see it here, all right, because of the y-axis. So going back to our question, can different network states have different or be characterized by different temporal ridge clubs? And we try to ask this question by basically aggregating, constructing an aggregated network within each of the states of the network states. Okay, so for instance, here S1 larger than K1 would be the group of nodes of interest in state 1. So this green state here, same for the other two states. And then what we can do is actually have a look at the state-wise cohesion of these groups of nodes. And here they are. We do explore also the maximal cohesion for different values of the relative aggregate degree in the corresponding aggregate network. And here we actually see, we look at the cohesion of, say, the groups with maximal values of state-wise aggregated degree. And you see that these 3 temporal ridge club patterns are actually very state specific. They basically occur just during one state. This is actually corresponding also to the overall temporal ridge club. And what's interesting about it is that if we zoom in and we look at these cohesion patterns here, we also find different kinds of temporal ridge clubs, right? You see that here there is something a little more quirky happening, and then we have a pretty high values of cohesion throughout the whole state. Here we have a rather persistent temporal ridge club throughout the whole network state, whereas, for instance, in state 5, there's even more temporal ridge clubs basically emerging at different moments in time, right? And what's interesting is that these groups of nodes basically have no overlap. So it's different nodes in different states. And so takeaway messages from this very last part is that the instantaneous cohesion is maximal precisely in terms of the corresponding state, and that we find different dynamics, despite the similarity in their static ridge clubs, actually, that you can see here. So, I mean, very quick mention, and we also looked at what happens when we look at epileptic rats in the same condition, and coherently with the idea that there is a more disordinate functional connectivity. So, for instance, the amount of mutual information between the firing patterns of 2 nodes being a measure of functional connectivity. There is a more disordered functional connectivity due to epilepsy. We see that in terms of temporal ridge clubs as well, because we do not have as highly cohesive temporal ridge club patterns. We see that they're much more variable throughout time, as you can see here, this being the cohesion of this group of nodes over here. And I mean, we also have just one state in this network, and we see that temporal ridge club doesn't even last. It's not as persistent as it was before, when we had temporal ridge clubs that would persist throughout the whole lifetime of that state. So I'm reaching the conclusions of my work. To wrap it up, we found that similar static ridge clubs can actually lead to different temporal ridge club patterns. We saw this by looking at actually disentangling, if you wish, the behaviors of hubs versus reliever airports in the air transportation network. And this tool enables us to differentiate between persistent, transient temporal ridge clubs, and just like other temporal structures that have been studied, like temporal motives, temporal cores, Also, the temporal reach club can have an effect on spreading processes unfolding on top of temporal networks. And we also saw that the emergence of temporal reach club patterns can be related or can even be exploited to explore whether there are periods of interest or network states throughout the evolution of a temporal network. Maybe one of the limits and also future directions of this work is that in this work, we only looked at the aggregate degree of nodes. What would happen if instead of the aggregate degree, we looked at the strength of nodes and we defined the weighted temporal reach club, so therefore defining an S larger than S, so a threshold on the aggregate strength of nodes instead of on the aggregate degree. And well, that's it. Oops, sorry. Thank you all for your attention.
Yes, great talk. I was wondering about the reshuffling procedure and it, like, because thinking about the brain examples in particular, there's going to be probably some like spatial correlation also. So are there temporal null models that can incorporate those things, or is that still like future work to be done, and did you try any other stuff?
We did try other things as well, because this was one of the questions I had by my viewers doing my Viva. I mean, what we didn't try, which is something that could potentially be done, is instead of using a randomized reference model in which we reshuffle the original data, is potentially using a computational model of the same mechanism and trying to disentangle the real data from or compare the real data to the model. That's one possibility. I mean, I understand that in some contexts it makes sense to use, say, more traditional ways to come up with new models for network science. I think that's the case for the first two data sets that we explored. In the third one, it is true that maybe that kind of reshuffling is not as biologically informed as others could be. So yeah, and I would also like to stress that basically what we did was trying. So the review that I was quoting before here, this one, it actually contains something like 55 different approaches to randomize temporal networks. So we tried several. In the end, we stuck with this because it's really the one that disrupts, preserves. It's the most conservative one. It preserves everything in the aggregated network and only disrupts the time ordering of the interaction. So really the simultaneity. So yeah.
Cool. I have some question about the functional connectivity.
Yep.
So what kind of functional connectivity method did you end up using, or did you try?
So in the end, unfortunately, it wasn't me who actually measured the functional connectivity, because this actually comes from even another work by a colleague of mine back in Marseille. But the measure was mutual information between parent patterns. So if you want some kind of Kullback-Leibler divergence between distributions of dots in the end, where the dots are, so you have so you have discretized time, you have vectors. These vectors have zeros at that time stamp if the neuron doesn't produce a spike, and you have a 1 if it produces a spike. So you have, what you do is you compute the mutual information between each pair of vectors of parent patterns. And the reason why we used anaesthetised rats is that this allowed us to take very long windows, because this allows us to sample the mutual information way better. One of the questions we had, for instance, for our first work on this data set was, why didn't you do this with, for instance, behavioral data? And one of the ideas is that, one of the answers is that you would need to find a different measure, because mutual information could not be sampled as well for such short time windows, because behavioral things happen, way faster than every 10 seconds, right? So that wouldn't be enough to actually properly sample mutual information. And so our answer, for instance, for that was, I think if we come up with a different measure, then yeah, all of this analysis is doable.